Hey guys, I'm not able to be with you because of softball, so what I'm going to do is do the last part of these bonding notes in video format, and they're very easy concepts, so you shouldn't be too detrimental not having me teach it to you in class. So where we left off is resonance structures. Now, you guys watched a video on resonance structures in class. It was that 5-minute kind of video that gave you a good visual representation of everything. And so what a resonance structure is it's where I can draw Lewis structures differently, basically. So an example here would be ozone. So you see ozone is written like this. Well, I could draw that double bond there, but I could also draw the double bond there. So you see how there's two different ways that I could actually draw that particular Lewis structure, and both of them are valid. They're both correct. If I have that, then that is what we know as a resonance structure. What's actually happening here, and that video showed this really well, is this double bond is not stationary. That single bond is not stationary either. Those are basically switching back and forth. You know how if I were to like take a pencil and just kind of wiggle it, you've ever done that before, maybe when you were younger, and you just wiggle, 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 wiggle. And so if that's the case, then it almost looks like the pencil like hasn't moved at all. So it's like combining or hybridizing those two bonds. So you have that basically happening here. Because of that, these bond links, these two bond links there are equal. And it doesn't look like they're equal on paper, but they are because of that movement back and forth. And not only are they equal, but they're not quite the length of a single or double bond. If you remember when we talked about bond length, single bonds are the longest. So let me kind of show that to you here. So single bonds are long, double bonds are a little bit shorter, and triple bonds are even shorter. Okay, and as you decrease your bond length, you're actually increasing your bond energy. So what that means is that it's harder to break those bonds, and if I'm forming that bond, it's more energy release. So it depends on whether I'm breaking it or forming that bond. So the relationship is bond length goes up, bond energy goes down. And so what we see in resonance structures is that they're equal in bond length, and they're kind of in between the length of a single and double bond. So resonance structures lengths, I'm just going to put a little R there, are in between. So they're shorter than single bonds, but they're longer than double bonds. And so we have to be able to talk about resonance structures on free response. It might compare something that is a resonance structure versus something that isn't. And so you'll have to discuss about how they might all have equal bond lengths, but the bond length of the resonance structure is somewhere in between a single and a double bond, whereas true single or true double bonds are not in the middle. They're either single or they're double. So you might have to justify that on free response. You'll see that when you do practice. One other thing that I want to show you, and this is on your Lewis structures, benzene is one organic molecule. We don't get into much organic, but it's an organic molecule that you need to know how to draw it effectively. So it doesn't really fit this format of our Lewis structure. Instead, we draw it organically. And so you'll see this every now and then. They love to ask questions about benzene and AP, so I want to make sure that you know what it is. So benzene, its formula is C6H6, and this is what it looks like. It's like a hexagon. Each little point that you see there are your carbons. So you see that there's 6 sides, it's a hexagon. So I have 6 carbons there. Now the hydrogens are just understood in organic structures. So you just draw like line depictions of what you have. So the hydrogens, the 6 hydrogens are understood there. Now you see that I have little lines inside this benzene. That is a double bond present. This is a single bond. This is a double bond, single bond, double bond. So you see how this is a resonance structure as well. Your double bonds are alternating, so it's double, single, and it can be drawn in this way, or it can be drawn with the double bonds on those. So you have resonance there as well. Just like before, you have your bond lengths are equal, and they're in between that of a single and a double bond. So that's what you need to know about resonance structures. All right, so I want to talk to you next is bond order. So bond order kind of talks about the conceptual part we just talked about. As bond length increases, bond energy decreases. They're inversely related. So it's giving it more of a mathematical sense. And it will help you understand these resonance structures of how they have bond lengths in between as well. So the concept here is it shows the number of bonding electron pairs. As bond energy value increases, the bond length decreases, which then causes the bond energy to increase. All right, so you have that up, down, up kind of relationship there. So the way that we calculate bond order, so this is the mathematical component to the conceptual. The way we calculate bond order is the number of bonds divided by the number of connections. And we're looking at the central atom here. So let's just get to it. If I want to figure out the bond order for this here, all right, so carbon, I look and see how many bonds I have. So there's 1, 2, 3, 4. So 4, divided by the number of connections. So the number of bonds is what's bonded to the central atom. The number of connections is the atoms that are attached to the central atom. So how many of those do you have? We'll have 1, 2, 3, 4. So 4 divided by 4 is equal to 1. If I have just single bonds there, guess what? I should find a bond order of 1. So what about if I was double bonds? Well, I should get a bond order of 2. So let's do the math just to make sure. Carbon, how many bonds does it have attached? 1, 2, 3, 4. Divided by how many connections it has. So that's 1 connection, 2 connections. So 4 divided by 2 is equal to 2. Well, what's the relationship between both of these? Well, as bond order increases, bond length decreases. We know that conceptually, and therefore the bond energy increases. Now, where do resonance structures fall in line here? All right, we said it was in between a single and a double bond. Well, this math is going to show that. So if I have oxygen, I have 1, 2, 3 bonds there, divided by number of connections. So how many atoms are connected? There's 1, there's 2. So my bond order that I get is 1.5. So this is mathematically showing that the bond length is in between that of a single and double bond there. All right, so when do you have to do bond order? How is that going to help you? If you like this mathematical approach, it can help you with a justification for resonance structures. Other than that, it might ask some multiple choice questions and say, which of the following has a bond order of 2? Or which of the following has a bond order of 1 or 3, bond order of 3. And so you have to know how to do that. We're going to move to formal charges next. All right, so now what we're going to talk about is formal charge. So let's say, for instance, I had you guys draw the structure for SO4 2-. So that's the sulfate ion. And let's say I had a few people draw their structure like this. That's actually supposed to be 2 dots. Some of these depicted as lines rather than dots. So wherever you see a line right here, that's 2 electrons. So some people drew as sulfate ion like this. And some people drew their sulfate ion like this. Well, we do the math, we count up all the electrons, and you guys use the same number of electrons, which is the correct number. Well, if you were to draw either one of these structures for a free response question, then you would be correct. You would get your points. However, one of these structures is better than the other. So the question is, how do I know which is the more correct structure? So that's what formal charge is for. Now, formal charge is not a question that is asked very frequently. It is definitely going to be on your unit exam, though, to test you on that. But they do like to ask it every now and then. And especially when you take organic chemistry, it'll help you for organic as well. So that's why I still teach it. So it is used to determine the best Lewis structure. So here's some things that you have to remember. What you're going to be doing is finding the formal charge for each atom that's in this molecule. And the sum of all those formal charges should equal the overall charge. So the overall charge here is -2. So when I find each individual formal charge, all of those should add up to be equal to -2. If I had just a neutral atom, then obviously all of those will equal up to be 0. If I had a +1 for my molecule, then all of those charges should add up to be 0.1 or +1. The next thing is to figure out who is your best Lewis structure. All of the atom formal charges need to be closer to 0. So whichever one of these, when I calculate, when each individual formal charge, the ones that are closer to 0, that depicts which is the best Lewis structure and which is the more correct Lewis structure. So let's get into it. How do we calculate formal charge? Well, formal charge is equal to the number of valence electrons of that atom minus the number of electrons that you see in the Lewis structure. Now, one thing we have to pay attention to, bonds only equal 1 electron. The reason why is because I have 2 electrons here, right? Well, one of this electron is being shared from oxygen and the other electron is being shared from sulfur. So we can't count it twice. We can only count each electron once. So that's why we only count bonds as 1 electron. So let's get into the math. So formal charge, let's do sulfur first. So first of all, we ask, what is the number of valence electrons that sulfur has? Well, if you know how to look at the periodic table correctly, then you would know that sulfur has 6 valence electrons. Then we look and see how many electrons it has in our Lewis structure. Remember, bonds only count as 1. So I see 1, 2, 3, 4. So 6 minus 4 is equal to 2. So that is the formal charge for sulfur in this Lewis structure. Now let's do the oxygen. Now you notice how all of these oxygens are single bonds. So all of those oxygens will be the same. The number of valence electrons that oxygen has is 6. And the number of electrons that oxygen has here is 1, 2, 3, 4, 5, 6. A bond counts as what? 1, so 7. So I see 7 here. 6 little dots, 1 bond, that equals 7. So my formal charge for that oxygen is -1. And because all of these are the same, they're all going to be -1. I think I might have said 1, but it's -1 earlier. So all of these should equal to be -1. Now, 6 minus 7, sorry, it takes me forever to write, -1. All right, now, first rule, in order to really verify if this is a valid structure or not, all of the formal charges should add up to be the equal the overall charge. So we need to have these equal -2. Well, +2 minus 4 is equal to -2. So this is a valid structure, but we don't know if it's the best structure yet because we need to figure out the formal charges of this other structure here. So let's dive into it. Sulfur, 6 valence electrons minus the number of electrons, bonds only count as 1. So that's 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. We already see we're to a good start, right? We can already tell that this more than likely is going to be the best Lewis structure because this formal charge of sulfur is 2, whereas this one is 0. Oxygen, let's do the oxygen double bond. I'm just going to put a little double line there. We have 6 minus oxygen is 1, 2, 3, 4, 5, 6. So that's also 0. So this one's looking pretty good. We have another double bonded oxygen there, so it'll be the same. And then let's look at the single bonded oxygen. So we have 6 minus 1, 2, 3, 4, 5, 6, 7. Remember that these little lines are just the way that my little notepad does it. It's supposed to be little dots. So that's -1. And we have another single bond. 6 minus 7 is equal to -1 as well. To make sure that this is correct structure, all of these have to equal -2, which it does, which is the charge that you have there. And which out of these two has the formal charges closest to 0? Well, that would be this structure here. So what that tells me is that is the best Lewis structure. So again, the only time when you have to do this is if specifically it gives you two structures in a free response. So this is only a free response question. They give you two structures and they say, which is the best structure according to formal charge? They have to say that word formal charge in there. You do this, you get easy points. Your justification would just be that, hey, that second structure that I see there, that has my formal charges closest to 0. You showed your math, and that lets you know that you have the best structure there. All right, so for the last thing of our notes, we're going to talk about bond energy. I have it left up on my board from double period, so I'm just going to show you that. All right, let me fix this webcam. Let's see if you guys can see what I have here, okay? So you're going to have to do some backwards work. It's okay, though. In order to figure out bond energy, remember it's delta H is what the bond energies are equal to. So delta H is equal to the bond energy of my reactants minus the bond energy of my products. I hope you can see backwards, mirror image. Okay, so it's always reactants minus products. We did this in thermochem. You guys were, I don't remember how you guys did it single period. I think you did pretty well. Double period, didn't really know how to draw those bonds correctly. So you need a little bit more work. But if you are working with bond energies, you have to sketch those bonds. Now that we've covered Lewis structures, you should be able to do a lot better job with that. All right, so what I have here is a formula. CH4 plus 2Cl2 plus 2F2 yields CF2SCl2 plus 2HF plus 6. Nope, that's a 2. That's a 2, sorry. 2HCl. And so you see how I have every single one of those little Lewis structures sketched out. Now, you're just going to be working with this. They're not going to like grade your Lewis structures there. So if you want to neglect the dots, that's okay. But you absolutely have to sketch out those bonds so then you can count how many different bonds that you have. And so in this particular one, I set it equal to delta H. All right, I have 4 CH bonds. So that comes from over there on the right. I have 2 CCl ClCl bonds, and I have 2 FF bonds. And where I'm getting that 2 from is from the 2 coefficient. And then you have on your product side CF2Cl. So you see how I have 2 Cl bonds, I have 2 CF bonds, and that all comes from that one structure right there. I have 2 HF bonds, and I have 2 HCl bonds. And those two are coming from the coefficients there as well. So it's very important to be able to sketch those bonds. I'm going to have to put this down. I don't like looking at me like that. Hold on just a second. You're going to have to sketch those bonds in order to do it. Make sure it's reactants minus products, and make sure you set it equal to delta H. Most of the time, you either have delta H and you have to solve for one of the unknown bond energies, or you have all of the bond energies and you're solving for delta H. So that's the last of these notes. All we have left in this unit is VSEPR, which is the geometries, and I have some really good videos. They're lengthy, but I promise that it will help you visualize these structures. So we're going to watch those videos. We're going to talk about it in class, and then we'll be getting ready for our tests. So hope this is helpful. I'll catch you on the flip side.